Everyone, hello and welcome to this session on keeping up. Okay, keeping up with the ASP. You already know Amit. He presented the lightning talk earlier. My name is Sumit Semwal, and I'm the senior technical lead for Android at Linaro. Our team at Linaro works on all things Android. So before we begin, just a trademarks disclaimer. And so, what's the agenda? Well, it's simple. I will talk about some of the many new features in AOSP in the recent past, and then Amit will talk about the enablement of these along with some gotchas and pain points that were there. A quick recap on Linaro and development boards and AOSP. So I hope some of you may know about Linaro and the work that we do in the open source ecosystem. We have been a very long time advocate of AOSP and development boards in it. We support AOSP on a variety of member dev boards. We do extensive testing, including CTS, VTS combinations, and with these we report and fix AOSP and upstream regressions. So that's why these dev boards are relevant and important for most of us and the work that we do. For years, we have been talking about the importance of dev boards in AOSP at different forums like Plumbers, ELC, Linaro Connect, etc. And at the EOSS in mid-23, Amit talked about the pain points and rewards of maintaining dev boards in AOSP. So we'll look at some of the new features that have landed in AOSP since then. Let's start with the boot process. So Android boot process, like many other things, is complicated and requires vendors to implement almost annually changing boot requirements. The developers recognize that, and as a result, they have abstracted the Androidisms of the boot process in an Android bootflow UEFI application, which they call Generic Bootloader or GBL. More details on the link there. But the idea is that any bootloader that supports running an EFI app and provides some basic requirements should be able to have an Android-enabled bootloader part. There are various EFI protocols that have been implemented and proposed. So if you're interested, go and have a look at those links there. Also related to the boot process, previously on Android systems, the specification of boot devices was via a platform-specific string. This proved to be very non-stable because things like sysfs paths can change, and suddenly your platform-specific string doesn't work. So across kernel upgrades. To help with that, support was added recently to system core to allow searching for boot devices via UUIDs, and this allows making booting from external devices also much easier. For me, this has been an exciting change in AOSP in recent times. The support of 16K page sizes in Android, starting from Android 15. This results in a 5 to 10% performance boost and about 9% cost on the space side. How it is achieved is with a page-agnostic OS view, so which includes doing runtime page size calculation, OS binaries are aligned to 16K page sizes, etc. And then with that, once an application is updated to be page-agnostic, then it can run without change on a 4K or a 16K page size supporting device. Now, the most optimal way it would work with file systems is if the file system block size was also the same as page size. So file systems like EROFS and FTFS have been made 16K block size compatible. The next relevant feature is something that is more relevant for folks that keep their device drivers while they're working on upstreaming them out of tree. So this is called the driver development kit. And it helps vendors to develop GKI modules against the GKI builds using the right tools like hermetic builds and correct resources like headers and makefiles. This helps them keeping the vendor modules easy to manage with GKI while they are working on upstreaming them. When we work with GKI, there are upstream kernel modules that are already upstream and but need to be built as modules. So those are signed and made immutable during freeze on the KMI, and then they can't be overridden by vendors. So basically, if you say take Android 6.12 kernels, then the upstream kernel modules are not mutable by the vendors after they've been upstreamed. These are called protected modules. And sometimes what might happen is vendors may have pushed out a basic support for a kernel module and later on added new features. But if they are within the KMI freeze time, then as protected modules, they cannot be overridden. To allow these new features to be available in existing products, for example, during an update, GKI provides the option of unprotected GKI modules. So they can backport these newer features that are upstreamed and still use in an update for a device that comes later on. These are called unprotected GKI modules, but the catch is they're treated as vendor or out-of-tree modules and have the same restrictions as KMI symbols for KMI symbols. Talking about these, how do we make sure that this atomic update happens? So there is a thing called DLKM, or dynamically loadable kernel module partitions in the Android system, which allows updating GKI and GKI modules independently of the rest of the partitions. And the protected modules then go in something called system DLKM, while the vendor and unprotected modules are put in vendor DLKM partition. A related thing around modules and module loading is parallel kernel module loading, which, as the name suggests, allows multiple independent modules, kernel modules, to be loaded in parallel. And a driver can advertise its participation and availability for parallel loading by setting a probe type of its platform driver to prefer asynchronous. More details on the link here. You may be aware of the Android shared memory, or ASHMEM, which was an Android-specific file descriptor-based shared memory. Now upstream has something called memfd, which provides pretty much the same functionality. And to allow to use that with Android, with AOSP, an ASHMEM compatibility layer for memfd was added, which allows your older apps to still be able to use an upstream memfd FD. As new GKI kernel branches are tagged, there may be some issues that are found during these merges to Android common kernel branches. And so they have started, the developers at Google have started keeping these erratas public. And this is an example of the latest Android 16.6.12 kernel code base and issues they found while merging. This is also something new, and it's been talked about at various conferences. So virtualization in Android. So AVF or PKVM, there is an overview link there. I can just talk briefly about it. So Android virtualization framework, it provides a secure and private execution environment for executing code in Android. PKVM is the KVM hypervisor, but further hardened to disallow host from accessing guest memory by default. And Google's implementation of AVF uses PKVM as the hypervisor, CrossVM as the VMM building block, and then various services are implemented on top of this. So this allows you to run, for example, you can run Debian in a VM on an Android device today. Recently, a new hypervisor driver is being upstreamed to support SMME v3 in PKVM. And there are also various how-tos in case you're interested in experimenting to how to use custom virtual machines, updatable virtual machines, and device assignment in AVF. You could go to the link and have a look at that. There is a full presentation next by Sarban on trunks table, so I'll just give a one-line introduction. There is a new development process for Android, which is called trunks table. And with that, I hand over to Amit, who's going to take you for the rest of the presentation.
Hello. Right, so in this part of the session, we will look into the technicalities and the realities of AOSP development from a device maintainer and developer point of view. Be the device part of AOSP or the device being hosted on the external repositories, we will cover both the cases. I'll share the common pitfalls that we encounter while working on AOSP, the struggles, the failures, the success stories. I'll talk about the subtle AOSP breakages, subtle upstream breakages, and our experiments with some of the new features that Sumit has just talked about. So this is what the AOSP reference board page looks like as of today. These reference boards are the hardware platforms that are used as reference for developing and testing Android open source project. These reference projects, they provide a starting point for the device manufacturers to build their own device. Right, so one of the most important aspect of supporting a big device, supporting a device in a big project like AOSP is to keep up with always churning changes. In this slide, I'll share the common pitfalls that we encounter while working on AOSP. I'll start with the most common one, which is related to the AOSP repo sync. At times, we run into random build failures, runtime failures, which are totally or which could be totally unrelated to the project that you have been working on. So this is most likely related to the AOSP repo sync timing. So it is advisable to resync the sources after some time or wait for the internal pre-submits to catch and fix the regressions internally. If the problem persists, then you know that it may be one or more device configuration that you may need to change based on the new changes which you have just downloaded. And then there are some core framework specific changes that need corresponding device configuration changes. The examples which I can think of is the transition from HIDL to AIDL. Another example which we ran into some time back is that the lib hardware UI Vulkan manager, there are a few changes which assume that the underlying Vulkan backend supports 2 or more queues for the full Vulkan framework to work. But it is not true for all the Vulkan drivers, at least some drivers which we have played with. So we could not switch to the full Vulkan support, and we fall back to using OpenGL backend for that. Keeping up with ever-changing build configuration is something which we need to look out for. If you maintain external projects, then make sure that the Sung properties or the Sung, just look out for the Sung changes. I know because I ran into a build failure and it took me a while to figure out that it's not the code base which I'm using, it is something which has changed certainly in the core framework that I had to take care of. The Bazel migration seemed to be, so it was a big hype like 2 years ago, 3 years ago, that everything will move to Bazel build systems because they wanted to move to more hermetic style of building. But as whatever I've seen so far, the move to Bazel is being limited to just GKI and GBL repos. Next up is tracking upcoming AOSP features. As the new features keep getting added in AOSP, the device maintainers have to take care of that. They don't necessarily have to implement everything, but it's good to have the core features or the important bits implemented, if not all. I'll start with GBL. So we talked about the GBL. We were actively looking into GBL since the inception time. We provided feedback. We were testing the half-baked things and everything. Because we have been bit by legacy bootloaders a lot. If you are working on an older device, you may be aware, or maybe you are lucky, but at least in our cases, our bootloaders did not get updates as much as we would love to, right? Android was keep changing bootloader requirements year after year, and starting from bootloader header version 2, 3, 4, then add the init boot. It seemed like for every solution, for every problem, the solution was to add one more partition. So again, so as Sumit mentioned, GBL is the generic bootloader boot flow UEFI app, which decouples Android-specific components from the vendor implementation. It is very promising. It is going to help a lot of devices and small ODMs to move away from locked implementations to the latest Android bootloader features. Once we found out that the GBL is in a relatively stable state, we enabled it for one of our devices in AOSP. Right, so the link is there. If you can just click on that, you will figure out how to enable it, the configurations which you need, and I'll not go into much details in that. Second up is 16K page size builds. We also added 16K page size build support for all of our devices. For those who are not aware of this, 16K page sizes do not support 32-bit apps. At least the source code which is in AOSP. I know that vendors will find a way to put some kind of layers in between so that you can run 32-bit apps. But if your product is based on AOSP, if you are playing with AOSP, then 16K is going to support only 64-bit apps. Okay, so we also ran into a bootloader crash while trying to enable 16K page sizes. It turned out that our bootloader is only 4K was only 4K capable. And luckily, we were not the only ones. And as we were discussing earlier, a quick graph in the build source code, we could figure out that, okay, there is a flag. If you just set it, you can just boot with, if you can set it to 4096, it will take care of the image loading part, and your bootloader don't need to worry about the user space build, whether it is 4K, 16K, or something else. Right, so recently there are few more system core changes which caught our attention. These changes simplify booting Android from external storage devices. If you are booting from USB disk, I mean, if you have tried it earlier, it was a pain. I mean, you cannot do it without changing the system core framework. Maybe you can, but at least I could not do that last time. So now, the solution is now, okay, so the existing solution is that there is a kernel command line you must be aware of, Android boot device, where you specify the sysfs entry. It will look for that path. It will again backtrace, and it will find the block device which is used to boot Android from. It works good, but what if you have a internal UFS device, internal UFS storage and internal eMMC storage, but you are trying to boot from external devices? What happens is that the platform devices gets enumerated first. So Android first stage in it will find the device. It will say, okay, this is the boot device, but it's because the sysfs entry is different, because you have set it for USB, not for the platform device. So it will not boot. It will just get stuck and it will time out. Now this new bootag, what it does is you can specify a partition UUID as an argument to this Android boot.bootpart UUID. It need not be any boot partition. It could be just any partition from that boot device. The logic is that it will trace back the boot device out of that, and it will make sure that it can boot from that external storage. Another thing here is that if you have encountered this or not, you cannot boot with multiple block devices which have this Android partition layout. For example, I have an Android device. The internal partition is at Android partition layout. I have plugged in a USB disk, or let's say MMC SD card. It again has AOSP partition layout. GBL will trip on that. I forgot to mention that. Yes, GBL will trip on that. Even Android will go crazy that, okay, what is happening? I have no idea why there are multiple duplicate partitions of super or user data. So now this approach, it fixes that. So that's, I think this is one of the main headlines of using this. The important point of using this partition UUID is that if you do this, then booting from external storage is going to be a little less pain. Sorry, I exaggerated a lot on this because I have run into issues. I have run into a lot of issues just because of this thing alone. And I'm really glad that the Chromium guys fixed it in AOSP. Next one is the HMEM. We recently saw a renewed effort from the AOSP guys, and they are moving away. A hint that they are now finally moving away from HMEM. HMEM is the shared memory driver. It is out of tree driver since 5.18, I think, but it is still maintained in Android common kernel because there are some legacy applications which depend on HMM IOC tools. So this compact patches which I'm talking about, they make sure that you can switch to memfd interface, which is already upstream, and those compact IOC tools will take care of running those legacy applications which depend on HMM IOC tools. Right, so tracking relevant upstream projects. Maintaining AOSP on dev boards is like maintaining a device on a regular Linux distro. So we have to make sure that the AOSP modifications which we do, AOSP specific modifications or new additions which we do, it should align, or I hope that it aligns with the upstream code base. For this session, I have listed down the usual projects like the Linux kernel, U-boot bootloader, Mesa, FreeReno projects. But the list can go on and on depending on the kind of features that are being supported on your device. I'll start with the frequent, I'll list down few breakages or few pain points which we encounter. The occasional upstream Mesa build breakages, it used to be a lot. Thankfully, we don't catch new ones. There are no new regressions maybe. I'm talking about the building upstream Mesa project. And then, right, so the GFX stream. So this is again a pain point. Graphics stream is the, I don't know if it's a graphics pipeline or it's a graphics subsystem. These are the changes which help in your virtualized displays, right? So the graphics stream changes, whatever they have done in AOSP, these are cross-platform changes, right? Which are very bad. You cannot have a dependency of one project on a different project, especially when the second project is an external project like Mesa, right? So we ran into a lot of build issues because of that. So we end up having hooks in between, and I hope that no one else have to deal with this. Sorry. Then our Linux breakages. There are a few Linux breakages which are specific to Android common kernel. We track core Android common patches like HMM, overlay FS for ADB remount, and DM default key for metadata encryption. We make sure that these patches don't break on almost every merge window. SysFS nodes, as everyone, sorry. So SysFS entries, SysFS nodes are not stable interfaces, right? So kernel developers have made it clear from day one that, okay, you can use SysFS, but don't rely on it because it's not a stable ABI. Android, however, uses SysFS a lot, right? SE Linux access control is based on your SysFS path. So if you just change anything, if you move from one kernel version to another, there's a chance that SE Linux may not like it. Another thing is that if you cannot reproduce a AOSP bug on a regular Linux distro, then it is very hard to sell, right? So the upstream developers, sometimes they can be very fixed on that, okay, I don't see this issue on my system or on my Linux distro, so is it even a valid bug? Next up is the firmware bug. We sometimes run into issues because of firmware. If it's an OEM signed firmware, then it's worse because then you know that you're completely logged on that. Recently, there's been a quite surge in the LTS breakages due to auto-select cherry picks. But in the end, we get to see the benefits of all the hustle and bug fixes and things when the Android release boots on your device with no additional changes. Well, mostly because we have been making sure that our devices stay in sync with AOSP codebase throughout the development cycle. Next up, I'm going to talk about maintaining. So I've talked about the devices which we maintain in AOSP, the features, we enable it, get done with this. How about the devices which are not part of AOSP, right? So I'm going to talk about maintaining or running AOSP on the development devices which are on external repositories, on your personal repository, on your local stations. And by the way, if you are an AOSP developer, which I'm assuming that most of us here are, and if you have not already joined this new AOSP systems developer community yet, then please do. We believe that this open collaborative initiative will be instrumental in information sharing and co-developing generic software solutions, and would be beneficial for the entire AOSP ecosystem. This is a snapshot from the website, and it lists a handful of devices and the projects that run AOSP reliably. Now, coming back to the main topic of running AOSP on external devices, all the pain points that we discussed earlier, this still holds for these as well. But the process, I think, is a bit relaxed. You don't need to stick to the GKI. If you are okay with having a standard defconfig-based builds, you can just stay with that. Again, some perks of running AOSP on an external device is there is no obligation to run or support AOSP main development branch. You can run a more stable GSI release branch and go on with your project. You can set custom sync rules in your local manifest. That will save a lot of download time as well as data usage. You don't need to worry about breaking other AOSP targets or breaking internal targets. It could be anything. You don't need to worry about namespace conflicts because you don't care about other projects, right, in AOSP. Okay, let's skip this part, sorry. Use these, we use these devices which we don't host in AOSP as an Android playground or for our proof of concepts. Speaking of using dev boards for AOSP playground and proof of concepts, I'm plugging in the dev boards for Android projects which we maintain. We maintain a few devices, few build targets outside of AOSP. We use it for our little experiments like running with the stream kernel, no Android changes, see if you can reproduce the bug or if you can do all sorts of things. You can play with all the things which I talked about earlier, right? The VKMS thing, the software rendering bits. We can just experiment on all these things. You can try the unified boot images and all those experiments. We use this workspace as a staging area for devices or features before pushing them upstream. That brings us to the end of this session. The summary or the key takeaway from this session today is that keeping up with the AOSP is hard. Let's work together to engage on common software solutions and join the AOSP developer community and help us improve the AOSP ecosystem.